In this video, we're going to take a look at section 8.3 on testing a claim about a mean. We will be using the same procedure that we have used for all of chapter 8 so far, the hypothesis testing process. So let's review the components of the hypothesis testing process. First, we need to identify the claim and write it mathematically. Second, we want to identify the null and the alternative hypothesis based on the claim that we were provided. Third, we will identify the value of alpha, which should always be given to you in the problem, and whether the test will be a left tail, right tail, or two-tail test. So that's something we'll have to determine based on the alternative hypothesis, I guess. Calculate the test statistic. That'll be the fourth thing that we do. Fifth, determine the critical value and or the p-value. And sometimes there's two critical values, by the way. There's always only ever one p-value, but sometimes there are two critical values if it's a two-tail test. Draw our initial conclusion, which is to either reject or fail to reject the null hypothesis, and then state the final conclusion about the claim. So that is the process we will use for testing claims about a population mean. Here are the requirements for testing claims about a population mean. Assuming that the population standard deviation is unknown, which should generally be the case. If you're testing a claim about an unknown mean, you most likely wouldn't know the population standard deviation. Now in chapter 7, we kind of had that discussion, and I think we did at least one example where we assumed we knew the population standard deviation. I don't think I'm going to do that in chapter 8. So for these problems, this should always be the case, that we don't know the population standard deviation, which means we will have to use the t-distribution in order to test the claim. So the requirements here are that the sample observations are simple random samples, and that either or both of these conditions are satisfied. The population is normally distributed, or the sample size is greater than 30. So n needs to be greater than 30. As long as one of those, at least one of those is satisfied. If they're both true, that's fine also. All right. Then you can use this process we're about to use and get valid results that are reliable, that you can trust. The test statistic for testing a claim about a proportion. Oh gosh, okay, I made that mistake again. I'm so sorry about that. I've been putting these together so quickly in the last couple of weeks, and so I've gotten, and of course, even if I wasn't trying to be quick about it, typos happen, and so first edition, you got a lot of typos. Then you go back, which I hardly ever do. That's my issue, is I don't go back and revise. So I need to go back, revise, edit, and change all these typos that I have. And obviously this typo has occurred because of copy and paste. So I just copied the slide from section 8.2, which is about proportions, pasted it here, replaced it. So the formula is correct. It's the right test statistic, but I forgot to change the title. So I apologize for that. So here's the test statistic for testing a claim about a mean when you do not know the population standard deviation. You want to use the t-distribution, and so you will get a t-score as your test statistic. It is the sample mean minus the mean of the sample means, which we will get from the null hypothesis, but maybe not directly. So remember, from the central limit theorem, if the sample size is bigger than 30, or if the population not standard deviation, if the original population, I don't know where I was going with that, if the original population had a normal distribution, then the mean of the sample means simply equals the mean of the original population. And so in fact, when I rewrite this formula as we go through these problems, I don't write this part of it because it simplifies to just the mean, which we get from the null hypothesis. So we're going to assume that the population mean is some value in the null hypothesis, and then that's what we're going to plug in here. And that just so happens to equal this because of the central limit theorem. All right, divided by s over the square root of n, which if you recall is also from the central limit theorem. This is what well, of course it should be sigma here, right? But this is what the standard deviation of the sample means is supposed to be according to the central limit theorem. So really, this is like your normal z-score formula, the data value minus the mean divided by the standard deviation, but adjusted for sample means. All right. And then the central limit theorem allows us to make that simplification here. And then here, we would like to use sigma, but we don't know it. So instead we use S, which is why we are now calling this, instead of a Z-score, it becomes a T-score. All right. So anyways, you don't need to know all that background information. You just need to know this formula. But I would consider just simplifying this to just mu. And that's the way I use it. That's the way I think of it. And I think it's a more useful way to write it. Okay, so let's take a look at some examples. According to the manufacturer, the normal output voltage is 120 volts. There's really not a lot of detail here, so I have no idea what has a normal output voltage of 120 volts. So I'm assuming it's some kind of machinery, maybe like a power tool or something like that. The 40 measured voltage amounts have a mean of 123.59 volts and a standard deviation of 0.31. That's from the sample, right? So this would be the sample mean. So that's X bar, right? That's the sample mean. That kind of looks like a chi-square. We'd have to be careful about that. All right, so let's try that again. Okay, so that's X bar and the standard deviation of 0.31, which is S. I'm having trouble writing already. So use a 0.05 significance level to test the claim that the sample is from a population with a mean equal to 120 volts. So 0.05, that's alpha. And then we're given this claim that the mean, that's mu, is equal to 120. All right. So we're going to go through the hypothesis testing process in order to get our conclusion about this claim. The first step in that process is to state the claim in mathematical form. So the claim here is that the mean, which again is represented with the symbol mu, is equal to 120 volts, but I'm just going to drop the units on the numbers. There could be some problems where you got to be careful with the units, but that's never the focus of the problems in this textbook. So I don't think they're going to try to trick us with, oh, here the units were in volts, but here they were in electron volts or whatever. I don't even know if those are like equivalent type of units, but we're not going to have to worry about converting or anything to make sure the units match up. So you shouldn't have to worry about that in this textbook anyways. All right, so that's the claim. The second phase is to set up the null and the alternative hypothesis. So remember, same as it was in 8.2, same as it was in 8.1. So this is the kind of our third iteration of going through the process of setting up null and alternative hypotheses. And while the details have changed, this time it's about a mean, and 8.2 is about a proportion, the rules for getting the hypotheses have not changed. So it's just another, it's repetitive. It's the same exact thought process, all right? So the claim has to become one of these. The null has to have equality, and the alternative and the null have to be opposites of each other. So if the claim has equality in it, then it must become the null hypothesis, at least initially. And then sometimes we will have to simplify. But this time, we don't even have to simplify. It's exactly what we want it to be. So the null becomes the claim, or I should say it the other way around. The claim becomes the null, which is that mu is equal to 120. And then the alternative will be the opposite of that. So the opposite of equals to 120 is not equals 120. Right? And so there is our null and our alternative hypothesis. All right. 3, identify alpha. Well, we already kind of did, but I'll go ahead and write it down here. Alpha is 0.05. That was given in the problem. And if it's a left tail, right tail, or two tail test, well, the alternative hypothesis is the shortcut for determining that. If it's not equals to, that becomes a two tail test. All right, and so it's a two tail test. So keep that in mind when that becomes relevant, which isn't quite yet. So the fourth step, the fourth phase here is to calculate the test statistic. And we're going to use that formula that we just had on the previous screen. So T equals X bar minus mu, which again, technically it's mu sub X bar, but the central limit theorem tells us that's just equal to mu. So I'm just going to simplify it to that, over S divided by the square root of N. So I think a simpler formula than what we had to do in 8.2. Right? That formula in 8.2 is a little more complicated. And we have all the information. So X bar is given in the problem. Let me use a different color here. So X bar is given in the problem, which is 123.59. It's just off the screen there. I can scroll up so we can see it. 123.59. All right. Minus mu, which we actually don't know, but the value that we're going to use for that is from the null hypothesis. All right. So we're going to assume the null hypothesis is true and that indeed the mean is 120 for the sake of argument, just to see how the sample compares, if that actually is the population mean. And does that give us a very extreme t-score, or does it give us a reasonable t-score? And that'll help us judge whether that assumption seems to be valid or not. All right, so we're going to assume that the mean is actually 120. Now, I kind of like this problem because these don't seem that different, right? I mean, like the discrepancy here doesn't seem to be that big if you just look at the means. But what you have to also take into account is the standard deviation, right? Which is 0.31. And remember, the standard deviation is measuring the variation in the data set. And for a mean of 120, to have a standard deviation this small means there is not a lot of variation in the data set. Now, if our data values were like in the 0.5 range, like if our data values are like 0.5, 0.1, 0.2, then this is kind of a big standard deviation relative to the size of the numbers in our data set. But with our data set having a value, like values around 120, having a standard deviation of 0.31 means it's very little variation there. So it shouldn't deviate much from the mean, right? If the mean is 120, this is actually quite a big deviation considering that the data set, the population, doesn't have a lot of variation. The standard deviation bears that out. It doesn't vary very much. And so if that is the population mean, this is actually quite a deviation from it, right? And it shouldn't be, now if the standard deviation was like 4, well, this is within one standard deviation in that case. That's not that surprising. But for it to be 0.31, how many standard deviations away is that? That's like 10 standard deviations away. That's significant. That's quite, extreme, given the data set and the fact that it doesn't vary that much with such a small standard deviation. So that's just my initial impression of like, and when I did, because we went over this in class on Thursday, and this is only my second time going through this particular problem since I'm redoing my notes and everything. I got new examples to do. And I was kind of surprised by the answer, but then after the fact, I was like, well, this actually makes sense. And so now that I've kind of gone through the process, I'm just sharing my insight with you before we do the calculation. But I didn't catch it before we did the calculation. It was only after the fact it caught my attention. And then I was like, what would justify? Because, if you get an answer that seems absurd, you have to kind of double check that to make sure, like, is this a legitimate answer or did I make a mistake? And so I wanted to justify the answer I got because the answer we get here is actually fairly extreme. Like, if I'm not mistaken, it's like the most extreme answer I've ever gotten. And it's almost stretches, beyond acceptability. Like, I kind of feel like it almost is unbelievable that this would be the answer. So I had to go back and make sure, like, did I make a mistake? Does this kind of answer actually make sense? So I'm thinking, if it's the one I'm thinking of. All right. So the sample size is 40. All right, I forgot to point that out. But the sample size is 40. That's given in the problem. And that's what we want to plug in here. Now, when I go to plug this into my calculator, we talked about this in 8.2 for that test statistic formula. The numerator needs to be in parentheses for the calculator to do the calculation correctly. But in this case, since the whole thing is not in a square root, we need the denominator to also be in parentheses. Otherwise, you might not get the right answer. So, all right, so let's go ahead and take parentheses 123.59 minus 120, close the parentheses, divided by new parentheses 0.31 divided by the square root of 40. Close the parentheses on the square root, close the parentheses on the denominator, and yeah, this is the one. This is the one that's just like, Because again, I don't know if students would see this number and think, oh, that's kind of alarming. But remember, because t-scores, they're a little bit different than z-scores, but they kind of are the same, you know. And a z-score we expect to be between -2 and 2. That's where most of your values will fall. 95% of your data values will have z-scores between -2 and 2. It's only the most extreme 5% that will have a z-score that goes beyond -2 or +2, right? And they have to be pretty extreme. We consider that to be extreme. So that's so keep that as your reference frame, right? Anything beyond 2 starts to become unusual, right? 3 is unusual. A z-score of 5 is highly, highly unusual because our cutoff is at 2. So again, that gives you a sense of the scale, right? You expect most of your data values to give you a z-score between -2 and 2. And if it goes beyond that, that's when you start to get the more unusual values. And the further away you go from -2 and 2, the more extreme it becomes in almost an exponential way. So again, 5 is really, really extreme. It's very, very unusual. You can actually calculate the probability. What's the probability of having a z-score that's 5 or more? It's very, very small. It's very extreme. So keep that in mind when I write this answer down, right? Here we get a t-score of 73. That just blows my mind, honestly. 73.24. I'm just going to go 2 decimal places on that. And so, yeah, I had to think about that because, like, I'm expecting 2, 3, somewhere in that area. In the extreme case, right, 3, 4, right, that'd be an extreme t-score. So 73 is just unheard of. It's astronomically large as a t-score. And so you should doubt that because, like, that is not a value that you should expect to see for a t-value. And so that's why I had to think about it. And I'm like, okay, well, actually, this does kind of make sense because the standard deviation is so small that we would not expect, if 120 actually was the population mean, then our sample mean should not venture very far from that, especially with such a small amount of variation, especially with a sample size of 40. That's another factor here, right? So we would not expect the sample mean to go very far from 120. So to have 123.59 would be really, really unusual if, again, this is a big if the actual population mean was 120, which we don't know that it is, right? We just assumed that it was equal to that without any evidence. And this seems to really indicate that that was a bad assumption because this should just never happen. You should never have a t-score like this. So this must not be the true value for the population mean. It must be closer to 123. That would make more sense. So anyways, just to give you a little bit of insight of like how we should be thinking about these numbers, right? 5. And even though that closes the book for me, like I just know that's so extreme that this is a bad assumption and I should reject the null hypothesis. I don't need to see the critical value to know that's what I should do here. But we want to be formal about the process we use. So we want to follow through the entire process and just be as formal about it as possible so that there's no questioning, right? So we followed all the rules and that's the conclusion that we come to, right? And so that means we need to get the critical value, right? The critical value is found using alpha. So just like in 8.2. So by this point, after we've gone through 8.1 where we talk about all the steps individually, and then 8.2 where we do several examples testing a claim about a proportion, I start to feel like this is really repetitive. I'm just doing the same things over and over and over. Now, the details are a little different, right? The test statistic is different, but that's about it, right? Everything else about this process really doesn't change. The claim is a little bit different with the symbol that we use, but setting up the hypotheses, exactly the same as what we did in 8.2. This part, exactly the same. Critical value, p-value, exactly the same, except it's a t-distribution. So that detail's a little different, but still, it's the same thought process, right? Reject or fail to reject, exactly the same. And the final statement, the final conclusion is done in the same way as well. So it gets pretty repetitive, which is a good thing. You know, you practice it several times and you get the hang of it because it really follows a script, right? It's very algorithmic And as soon as you learn that algorithm, you're good to go. So now to get the critical value, we use alpha, but this time we have to divide the alpha by 2 because it's a two-tail test. We have to cover both the left tail and the right tail. So we take the alpha that we're provided, we divide it in half to cover the left and the right tail. So we have 0.05 divided by 2, which is going to give me 0.025. And that's the area that goes into the left tail, and that's the area that's going to go into the right tail. And so we will have 2 critical values this time. So I wanted to find the t-score associated with that area. So I will use inverse t this time because we're talking about the t-distribution. The area to the left is 0.025. Sorry, I guess I was writing too fast. 0.025. And then we need the degree of freedom this time. So anytime you're doing the t-distribution, you have to use degree of freedom, which remember, at this point, now in Chapter 9, this is going to change a little bit, but at this point still, the degree of freedom is simply just 1 minus the sample size. Sorry, I said the wrong number. The sample size minus 1. I said the right number, but in the wrong order. Right? So the sample size minus 1, which is going to be 40 minus 1, which is 39. Right? So that's my degree of freedom, which I'm going to need for the p-value also. So this kind of helps with both tasks. All right, so what am I going to get here? Now this is for the left tail. We get inverse t, which is 0.025, comma 39. Takes a minute to calculate, and I get negative 2.023. I'll just go 3 decimal places on this. Now that's the critical value that's in the left tail. For the right tail, it also has a critical value associated with that area, but because of the symmetry, we know it's going to be the same number, but positive, right? So also 2.023, positive 2, right? So these will both be my critical values. So I don't have to recalculate the second one. It's the same number, but because it's in the right tail, it's positive, right? So those are my critical values. For p-value, you want to take, and this is going to be a little bit of a silly exercise too, you take the test statistic. Now remember, 0 is in the middle, so the test statistic of 73 would be really, really far into the right tail, but I'm not going to, to draw that realistically, I would have to go way over here. It'd be over here somewhere, right? So I'm not going to bother making it that realistic. And because for the problem is this has to keep getting closer and closer and closer, and I'm not going to be able to draw it the right way. So I'm just going to put it right here. And we want the area, because it's a two-tail test, we want the area to the closest tail. The closest tail here is to the right, so we want the area to the right. We want that area there. Why am I putting normal? I made a mistake. We want TCDF, right? Because it's the t-distribution. I almost put normal CDF. We want TCDF. The lower bound is 73.24. You might say, well, did I round too much? It's not going to matter here. This is going to be such a small area, it's practically equal to 0. The upper bound is infinity. And remember, for the t-distribution, you have to give the degree of freedom, which is going to be 39. All right, so let's do TCDF. It's under the distribution menu, which you get on the TI-84 by doing second vars. TCDF. We have 73.24, comma 9999999, a bunch of 9s, comma 39. And I get negative 1.95 times 10 to the negative 17. Now the funny thing is, when we did this problem in class, I think this is what my students got. And I got negative 1.95 times 10 to the negative 23rd. And it might be a difference of how many 9s we used to represent infinity, or it might be a difference of how many decimal places we carried out the test statistic. And that really is a big difference. Times 10 to the negative 17 is, an order of magnitude of 5 difference than 10 to the negative 23rd, right? That's an extra 5 zeros that go into the decimal places between those two numbers. So that's not anything to scoff at. That is a significant difference that we should, in some cases need to be careful about. In this case, we really don't. So this is the area. Now, because it's a two-tail test, remember what we have to do. We have to double this. So we're going to multiply that by 2, and I'm going to get negative 3.9 times 10 to the negative 17. Which, if you write it as a regular number... Oh, that's the weird thing about this. Okay. Well, that was weird, and I meant to talk to my colleague about this because... And I've totally forgot about this. And it's kind of embarrassing that I'm having to, notice it again live on my recording that I really don't want to have to go back and edit out. That was one weird thing, that our exponents were different. And I don't know, again, I told you why that might be the case. But then, and this is really the same way it happened to me again, in class is what's happening to me now, is I don't notice it at first until I multiplied it by 2. And then I'm like, wait a minute. This is negative? Now, critical values can be negative, and maybe that's why I kind of let that pass. But areas cannot be negative. But that is indeed what my calculator gives me, and that's what my students got too. So, it's not a mistake I'm making. It's a mistake the calculator's making. And I have to attribute it to, this was my explanation to my class, because I was like, that shouldn't have happened. And it's not, I don't think we did anything wrong. I think it's whatever process the calculator uses to calculate this area obviously breaks down at some point, because you shouldn't be getting these kind of t-scores. These are like not really realistic t-values. 73 is just not a t-score that makes any sense, really. It's just such a big number that you never should see a number like that. All right. And so I think because that's such a large number, the calculator just doesn't handle it correctly. Whatever algorithm it uses to calculate this area obviously stops working at some particular value of t. And it works in the usual cases that you normally would see, but in these extreme cases, obviously it produces a result that doesn't make sense. It shouldn't be negative. And so my interpretation of this was that the calculator, when it calculated the area, went past 0. What probably happened, actually, now that I think about it, is what I actually drew on my picture here, which is whatever they use in the calculator to estimate this t-distribution, it must dip below the x-axis at some point, I guess. And then this would count as a negative area. So you take the positive area minus the negative area, and that's why it might be coming out negative. I think that's kind of how the calculus of that would work. But I don't think that's supposed to happen. So I think it just must be an artifact of the way that the calculator is doing the calculation. Either way, what I told my students was just put 0. It's such a small area that the calculator couldn't even handle it and ended up thinking it was a negative area, right? Which just gives you an idea of it became so small that it went negative, right? And so it's 0. I think we should just put 0 there for the p-value, which again, we should double, but when you double 0, it's still 0, right? So the area is 0. All right, so sorry that happened. That's really a weird quirk. I never had encountered that issue before until in class on Thursday, and then now again in this video. It feels like for the first time again, but that shouldn't happen. You shouldn't get t-scores like this on any of your problems, and you shouldn't get negative areas. And if you do, just say the area is 0. I think that'd be a safe way to handle that. Okay, so 6, reject or fail to reject. Right. So if we use the critical value method, we are drawing lines on the left and the right tail at negative 2.023 and positive 2.023. And so if our test statistic crosses either of these lines, we will reject the null hypothesis. If it doesn't, if it stays in between, we would fail to reject. But if it crosses either line into either tail, we're going to reject the null hypothesis. And again, it dramatically crosses that line, right? 73.24 is going to be really far into the right tail. And if it goes anywhere past that line, we reject the null hypothesis. Or if it went too far into the left tail, we would do the same, right? For the p-value is less than alpha, right? The p-value is practically 0. Alpha was 0.05, and so the p-value is less than alpha. In that case, you should reject the null hypothesis. All right, so what do I conclude then? What do I say about this claim? So we will say that there is sufficient evidence to warrant rejection of the claim. So let me type this out. There is sufficient evidence to warrant I'm sorry, I don't know why I put a G in there. Rejection of the claim that the mean voltage is 120 volts. The reason that's the conclusion is because we're rejecting the null hypothesis, which is the claim, right? Remember at the beginning, the null hypothesis was the claim, right? I should say it the other way around. The claim became the null hypothesis. So any conclusions that we make regarding the null hypothesis apply to the claim as well because they're the same statement. If I reject the null, I'm rejecting the claim, right? And so that's exactly the conclusion I chose here. There's sufficient evidence to warrant rejection of the claim. So the mean is not 120 volts. The sample we have makes that pretty clear, along with the sample size and the standard deviation that we had. So, all right, let's take a look at another example. Listed below are heights in inches for the simple random sample of supermodels. Use a 0.01 significance level to test the claim that supermodels have heights with a mean that is greater than the mean height of 63.8 inches for women in the general population. Given that there are only 10 heights represented, can we really conclude that supermodels are taller than the typical woman? All right, so we'll get to that last question at the end after we go through the process, because even if we feel like, oh, we can't really conclude anything from this, we still have to do the problem that they've presented to us. So, so in this problem, rather than telling us the sample mean and the sample standard deviation, they just give us the sample, right? So here we have the sample of 10 supermodels' heights, which, oh, I didn't see that 0.5 on that last number. So I paused the recording to take a little bit of a break. And then I was like, oh, I'll just go ahead and type these numbers in while I'm, paused. But I didn't see that last number. Uh-oh, what did I do? Okay, sorry. This is what I was trying to avoid, you having to sit there while I fiddle around on the calculator. Okay, so let's redo that. All right, so what you're going to have to do in this case, if they don't tell you the sample mean or the sample standard deviation, but they give you the sample instead, is you'll have to determine the sample mean and the sample standard deviation. Now, a lot of students will say, okay, no big deal. Sample mean, add up the numbers, divide by the total, or in this case, divide by 10, which is fine. That's correct. That'll give you the sample mean, but you also need the sample standard deviation. And I don't think you really want to do that by hand, even though we went over that back in chapter 3. What we have opted for since then was to use the calculator to let it calculate the mean and the standard deviation for us if we give it a set of numbers. And so you do that using 1var stats. So it might have been a while since you've used 1var stats. So remember, you go to the stat button on the TI-84 and then you scroll over to the calc menu and 1var stats is right at the top. And then so you select that and then you also let it know which list to do the 1var stats on. And so, and then it'll give you several pieces of information, but 2 of which would be the sample mean and the sample standard deviation. And so I come up with, for this sample, I get a sample mean of 69.825. Let's keep all the decimal places for that. And a sample standard deviation of 0.7. It's going to round up to 8.8. So I was going to go 3 decimal places again, but it's 0.7997. So that 7 would round that 9 up. So it rolls over to 0. Carry the 1 over. That 9 bumps up to 0. And so it's going to be a cascading effect of, it's just going to end up being 0.800. Now you might say, well, do I have to keep the 00? Not when you type it into your calculator, but it is good to present that with the extra zeros because it lets whoever looks at that know that you calculated this correctly to 3 decimal places. Because if you just leave it as 0.8, somebody might think, oh, you just rounded to 1 decimal place, but that's not true. We rounded to 3 decimal places. So by keeping these extra zeros, it lets people know that we calculated it out to 3 decimal places accurately. They happen to be zeros here. So, okay, so that is the sample statistics that we need to do this problem. So, and n is equal to 10, right? I guess that's also going to be important. Alpha is 0.01 in this case. And the claim is that the mean height of supermodels is greater than 63.8. And they're explaining why that number was chosen, right? 63.8 is the mean height of women in the general population. And so that's why we want to compare it to that number. But you don't have to include anything in reference to that when you state the claim. The claim is just that the mean supermodel height is greater than 63.8. Right. So let's go ahead and write that down actually. So phase 1, the claim is that the population mean, but this population we're talking about is not the general population. It's the population of supermodels. Their height is greater than 63.8. All right. And so that's the claim. Step 2 is to formulate the null and the alternative hypotheses. Same process as before. The claim needs to become one of these statements. The null has to contain equality, so the claim can't become the null, which means it has to become the alternative hypothesis. So the alternative would be that mu is equal to, not equal to, mu is greater than 63.8. As I said equal out of my mouth, my hand was writing greater than, so I don't know how I managed to do, because I'm horrible at doing two things at once. My mind doesn't work that way. It can't multitask. It can't have multiple threads of thoughts going at the same time. I can just do one thing at a time. So I don't know how I managed to do that. And the null should be the opposite. The opposite of greater than is less than or equal to. And so we get the equality in the null hypothesis either way. As long as if the claim doesn't have equality, you put it as the alternative hypothesis, then when you take the opposite of that, equality will show up in the null like it's supposed to. Now, this is the traditional formulation of the null and the alternative hypothesis, but the new fashion is to simplify the null to just equals to. And so what you'll want to select as your answer on MyStatLab is, for the null hypothesis, it's mu equals 63.8, and the alternative hypothesis doesn't change. Right? It's going to be mu is greater than 63.8. So this is the answer that you want to pick. All right. So phase 3, identify alpha. In this problem, it was 0.01. And whether it's a left tail, right tail, or two tail test, you look at the alternative hypothesis. Greater than means this will be a right tail test. All right. And so that's phase 3. I guess I usually do this work over here. Phase 4 is to find the test statistic, which will be the mean, sample mean, minus the population mean over S divided by the square root of n. We identified many of these values in one of our stats, but the one we didn't identify is the population mean, which we actually don't know. But the value that we're going to use for the population mean is from the null hypothesis. So we're going to assume that the null hypothesis is true, that mu does actually equal 63.8 without any evidence. We're just assuming it for the sake of argument. So we're assuming that supermodels have a mean height of 63.8. Now, yes, the claim didn't say that, right? But to do the hypothesis testing, this is just how things have to get formulated, right? So our claim was actually that the mean height of supermodels will be greater than 63.8. But to set up the hypotheses, the thing we end up assuming is that the mean is actually just equal to 63.8. And then we're going to see how that compares to the sample that we have. Right, so here's our sample mean, sample standard deviation, and all those numbers are going to get plugged in right there. So maybe I'll scroll over so we can kind of keep everything on the screen while we plug these numbers in. So the sample mean is 69.825 minus the population mean we're assuming is 63.8 for the sake of argument. What happened there? Okay, 63.8, right, divided by S, which from the sample was 0.8. Now, on paper, it's good to keep the extra zeros, but in a calculator, it's not going to care about those extra zeros, so we can just drop them. Divided by the square root of n, which is 10. Right. Now, remember when we type this into our calculator, I should have left myself a little more space on the other end here. You want to use parentheses around that, and also parentheses around the denominator, right? So we're going to have parentheses 69.825 minus 63.8, close the parentheses, divided by the denominator, parentheses, 0.8 over the square root of n, which is 10, close parentheses on the square root, close parentheses on the denominator, enter, and we get another phenomenally large value for t, right? Just shockingly large. I don't know the right word. Maybe phenomenally wasn't the right word there. 23, not as bad as the first problem, but still pretty bad. 23.82. Now I can't remember because I did this problem in class as well. The one I didn't do is the next problem we're about to try. It'll be my first time doing that next problem, so hopefully everything goes smoothly. I don't remember if this gave a negative area. So this is pretty wild, right? I mean, so again, positive 2 for a value of t is kind of the edge of what you consider ordinary. And sometimes you'll get some extraordinary values, like t equals 3, t equals 4. Those are extraordinary, right? Those go beyond the ordinary. They're unusual and even kind of extremely unusual. But you rarely, and I would say like the normal extreme case would be like 6. That's about as extreme as these should get. So anything beyond 6 is just, you never see. It just you hardly ever get numbers like that for t. So this is another one that's really quite extreme. And I'm saying that, and maybe on the homework I'm wrong. Maybe this is a homework problem and you might get values like this on the homework. But I think these are fairly unusual. Like they're not just, they're unusual values, right? I mean, so like the usual unusual values would be like 2, 3, and 4. Those are unusual, but those are your typical unusual values. These are atypically unusual. So anyways, 23.82, again, that seals the deal right there. You know for sure that we're going to reject the null hypothesis. That's just really extreme. But we still want to follow the rules, follow the procedure, right? So 5, it's kind of like if you know somebody's guilty of a crime, you still try them in court. Even though it might be clear beyond a shadow of a doubt and they've admitted and all the evidence is just obvious to everybody, you still go through the process of trying them in court because you just want everything to be done exactly the right way, for the sake of justice in that case. So we do the same thing in statistics, right? Even though that number tells me all I need to know, I still want to follow the proper procedures so that I've done everything properly and there can be no questioning the results, right? So the critical value, in this case, there's only going to be one. It's a right tail test, so all of the alpha goes into the right tail. So all of this alpha here just goes into the right tail. So we have 0.01 in the right tail. We want to find the t value associated with that area. So we're going to use inverse t. We're going to use the area, which is supposed to be the area to the left, but remember we have this kind of shortcut we can use. Because of the symmetry, we can treat this as if it was the area to the left. It's going to come out as a negative value. But the number's still good. We just drop the negative sign, right? Because we're in the right tail. We want the number to be positive. So the number will be right, but the sign's going to be wrong. We just drop the negative sign and it'll give us the right number. We also need the degree of freedom, which is n minus 1, which is going to be 10 minus 1, which gives me 9. Right? And so that's what I type into my calculator. I'll get inverse t 0.01, comma 9. And we get, so again, I'm just going to tell you what I get in my calculator, negative 2.82, but I drop the negative sign. And that's going to be my critical value. Positive 2.82 because it's in the right tail. So again, it's the right number, but the wrong sign because we didn't do the area to the left, we did the area to the right. But the symmetry allows us to get away with that. We just have to be careful to remove the negative sign after we get our answer. If you don't like doing it that way, then the proper way we should have done this is to find the area to the left, which is going to be 0.99, right? 1 minus the area to the right gives me the area to the left. And then I should use that in my inverse t, degree of freedom 9. And it's going to give you the same number, but it'll come out positive that time. That way, you just take the number as is in your calculator. You don't have to worry about dropping the negative sign. So this might be something you want to look out for as you're doing the homework. If you find that when you try to use the shortcut, you always forget to remove the negative sign and you keep getting the wrong answer, maybe you shouldn't use the shortcut. Maybe you should do it the proper way, which is find the area to the left first and then use that in your inverse t. And the answer you get is the right answer. You don't have to do any modifications, right? The p-value, again, this is going to be 0, but I'm kind of curious to see if it's going to end up being, it'll be practically 0, I should say. It's not going to be exactly 0, but I'm curious to see if it comes out negative. So again, we want to find the area associated with this test statistic. Whoops, I put 2 8s for some reason. 8, 2. In this case, we find the area to the right because it's a right tail test, not because it's the tail that's closest by, but because it's a right tail test. And I don't know if I've mentioned this already, but sometimes there are problems where it's a right tail test, but the test statistic is actually over here by the left tail. It's pretty rare, but that can happen sometimes. And even though the test statistic is closer to the left tail because it's negative, you still need to find the area to the right if it's a right tail test to get the right p-value, right? So just be careful. Right tail test, always find the area to the right, regardless of where that test statistic is located, right? And so this is going to be TCDF. The lower bound is 23.82. Try that again, 23.82. The degree of freedom is 9. And let's see what we end up getting here. So TCDF, 23.82. Oh, I forgot. Wow, I just really blinked out there, didn't I? Maybe you guys caught this mistake. I forgot the upper bound. I went right to the degree of freedom. So my apologies for that. Upper bound should be infinity, right? And then 9 should go next. So, and I caught myself as I was typing in my calculator. I'm like, wait, I don't want the degree of freedom. I want infinity, which is 9999999, right? Comma 9 for the degree of freedom. And so this time the area does not come out negative, thankfully. So we get something that's more realistic here. 9.67 times 10 to the negative 10. So it's very, very small. And if my stat lab asks you to round to the 5th decimal place, 4th decimal place, this just rounds to 0. So again, it doesn't actually equal 0, but it's so small that it's practically 0. It's point. The negative 10 means we're going to have 9 zeros in front of this 9 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This will be... so that gets us, I don't know how I want to say this. You're taking this decimal place and moving it to the left 10 times. So you clear the 9 first, and then, so that's 1. And then you're going to have to go 9 more times. Those will all be zeros. So that's how you get 9 zeros there. So 967. That is the p-value. You don't have to double it because it wasn't a two-tail test. So this is the p-value here. Which, like I said, if they ask you to round to 4 decimal places, 5, 6, this is just going to round to 0. So that may be what you end up typing into my stat lab if this was your homework problem. All right. So what do I conclude? Well, we already kind of talked about that, but the conclusion is we will not fail to reject. Said the exact opposite answer. We will reject the null hypothesis. Sorry about that. Okay. So if you use the critical value method, our critical value is 2.82. If the test statistic crosses that line further into the right tail, we reject the null hypothesis. And it does, right? It more than crosses it. It goes really, really far past that line. So we're going to reject the null hypothesis because of that. For p-value, we compare that to alpha. The p-value is practically 0. Alpha is 0.01. The p-value is less than alpha, so we reject the null hypothesis. So our final conclusion then is going to be that we should say what about the claim? There is. Is it sufficient evidence or not sufficient evidence? Well, in this case, even though we are rejecting the null hypothesis, we are actually showing that the alternative hypothesis is true, right? If we're rejecting the null, we are accepting the alternative as a true statement. the claim was the alternative hypothesis. We are accepting the alternative, which means we are accepting the claim as true. Right? If the claim had become the null hypothesis, then we would have a repeat of what we did in the last problem, which is if you reject the null, you reject the claim. That's only if the claim is the null hypothesis. But that wasn't the case in this problem. In this problem, the claim was the alternative hypothesis. So by rejecting the null, we actually support the alternative, which means we support the claim. So there is sufficient evidence to support the claim that, what was the claim about? The mean height of supermodels is greater than 63.8 inches. Right. That makes it a complete sentence. And so that would be the claim, the conclusion, the final conclusion about the claim. All right. And so this is step number 7. All right. Now the last question in the problem is, can we trust this result basically? Even though the sample size was 10. Now, my concern was the sample size probably, I don't know, it depends. It really kind of depends. So I'm not sure if this is on MyStatLab, they should have some options, and it kind of depends what they want to focus on. The two things you should be concerned about are, is the original population a normal distribution? Now, the heights of women in the general population is a normal distribution. But are the heights of supermodels a normal distribution? I actually don't know. It may not be. It may not have a normal distribution. So that would be something we'd need to find out. Are the heights of supermodels normally distributed? Because if not, then no, this actually would not be a valid conclusion. Because remember, to use this process, either the original population has to have a normal distribution or the sample size needs to be at least 30. And it wasn't at least 30 this time. So the only way this will be valid is if the original population has a normal distribution. So, are the heights of supermodels normally distributed? If so, then yes, this seems to be a valid result. If not, then no, this should be questionable. This may not be valid. The other concern I have is, was the sample a simple random sample? I don't remember if they said or not, if it was. So, let me look up here real quick. Oh, okay, it is. Listed below are heights for the simple random sample of supermodels. So, it is a simple random sample, so that's not the issue. So the issue would be, do supermodels have heights that are normally distributed? And so I would read the question. Now, if it says the heights of supermodels are normally distributed, so yes, we can trust the result, that seems like a valid answer. If it says the heights are not normally distributed for supermodels, then, and so we can't accept the answer as true or as valid, then that seems valid as well. The other thing you could say is we don't know. And because we don't know, we really can't trust these results. That would also be a valid thing to say. Because really, you only want to use this process if you know that the original population has a normal distribution or that your sample size is bigger than 30. So if we don't know that our original population has a normal distribution, we would want a sample size bigger than 10. We would need it to be bigger than 30 in order for us to be able to trust our results. So those are my thoughts on that last question. But the correct answer on MyStatLab really will kind of depend on what they choose to focus on in the answers that they're providing. So let's look at, we have one more example to look at. Okay, last example. Listed below are the measured radiation emissions and W per kilogram. I feel like I should know what that is, but I don't know what W represents. Corresponding to a sample of cell phones. Use a 0.05 level of significance to test a claim that cell phones have a mean radiation level that is less than 1.00 Ws per kilogram. Okay, so I have to say I paused the recording for a second and then I did not type these numbers into my calculator. So let me pause one more time, type the data set into my calculator so you don't have to sit there and wait for me to do that. But remember, we type this data set into a list on our calculator on TI-84, run the 1var stats so that we can get the sample mean and the sample standard deviation, which we're going to need to do the hypothesis testing. So just give me 1 second. Okay, so assuming I type the numbers in correctly, I end up getting a, a sample mean, sorry, my computer is making a funny noise. I don't know if the mic picks it up or not. Of 0.938. I don't know how many decimal places to go with that. I guess one more than what's present in the original data. So we have 2 decimal places here. So going 1 more decimal place than that would be good. Okay, so 0.938. The standard deviation I find for this sample is 0.423. And the sample size is 11. Right, so all of that can be found in one of our stats. Alpha is equal to 0.05, and I think we're ready to go. So we have the claim here that the mean is less than 1. And we don't have to worry about the units. Like I said, they're not going to try to trick you with that. So the claim is that the mean is less than 1, 0.00, but we can just write that as 1. I don't know. I guess if it's on MyStatLab, they might want you to actually type it in like that. So maybe I should do it as you would need to get it right on MyStatLab. Okay, so that's step 1. Step 2, hypotheses. So there's the null. There's the alternative. The claim has to become one of these statements. It doesn't have equality, so it will have to become the alternative hypothesis, which means the null will be the exact opposite of that. The opposite of less than is greater than or equal to 1.00. And then we will simplify the null hypothesis to just equals 2. And so this is the answer you would want to select on MyStatLab. Now, the way I'm going through that process might be a little different than what you'll see if you look at the question help. So I can do I can't even do a less than symbol at this point. Okay, there we go. So if you look at the question help on MyStatLab, they might have different suggestions for how to get to this answer, but this is the way I prefer to do it. And it kind of is based on the history of how this traditionally was done, which is the way I'm used to doing it. But it's fine. If you want, what I was going to say, I'm like, why am I even bringing this up? So if you want an explanation for this, if you go back and look at the video for section 8.1, I kind of spent some time talking about how this was formulated, why this makes sense, why it's done this way, and why I feel like it's still important to think of it this way, but how the new fashion is to simplify the null hypothesis, which there's a good reason for that too. But I think you kind of miss something by doing that. You kind of, leave out, how should I say this? I can't even think of a good way to put it. Something is missing when you just write it like this. There's a aspect to the problem that kind of you miss out on if this is how you write it and you never think of it like this. All right, I guess that's the best way I can think to word it. Anyways, let me stay on track so we can get this video done. All right, 3, alpha was equal to 0.05, I believe. And this one will be, this is a less than, the alternative is a less than, so it'll be a left tail test. All right, the test statistic, t equals the sample mean minus the population mean over s divided by the square root of n. We will get the population mean from the null hypothesis. We're going to assume that the null hypothesis is true, and that's what we'll plug in for mu. Oh, I just cannot draw arrows very good here. Let's try this again. All right, so that's what we'll plug in here. And then the rest of this, the rest of these variables, the rest of these numbers come from the sample, right? And so it's all these numbers up here. And so all of these will get plugged into the test statistic as well. And that'll give us our test statistic. So let's go ahead and I'll just scroll over this way so we can kind of have all the numbers on the screen as we're plugging them in. The sample mean is 0.938 minus the population mean. We're assuming that's 1.00 over S, which is 0.423 divided by the square root of n, which is 11. I will type this into my calculator. I have to use parentheses for the numerator and parentheses for the denominator. I'm sorry, I can't let that go. Let's try that again. Okay, that's a little bit better. Okay. And so let's see what we end up getting. So I have parentheses 0.938 minus 1 divided by parentheses 0.423 divided by the square root of 11. Close parentheses on the square root, close parentheses on the denominator, and I end up with a test statistic of negative 0.486. I'm going to go 4 decimal places on 1. All right. And so that'll be my test statistic for this problem, which is a very ordinary looking test statistic for once, right? The first 2 problems we had were extraordinary in a large degree, right? Again, I struggle, in this day of hyperbole, it's hard for me to find wording to really describe how extreme those previous 2 t-scores were. They were very, 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 very unusual, and how large they were. They were very large values. This is very, very, very ordinary, right? This is a very typical, again, between -2 and 2 is what you typically get from most values in your data set. So this is what you would expect to get. If the mean was 1, you expect to get samples like this because, this number reflects that assuming that the population mean is 1.00, this kind of a sample is a pretty typical kind of sample that you would get, especially given that standard deviation there, right? And so, and that's what the t-score is letting you know, that given that assumption, this sample looks pretty ordinary because you get a really ordinary looking t-score, right? So I'm not very doubtful of this assumption because the sample looks pretty ordinary in the light of that assumption. Right? Okay. Now, another thing I noticed when I'm watching my videos, I've been editing a couple of them recently, and I've noticed that I say right a lot. I'll kind of say, kind of as a filler, transitioning from one thought to the next. And it kind of was bugging me. So I don't know if I can do anything about it. But just acknowledging that I know I'm doing that, and I'm sorry. Okay, critical value. Now, I'm pretty sure about the conclusion here. That's so ordinary that I would not expect to reject this null hypothesis. I don't think that assumption is a bad assumption at all. But we want to follow the procedure just like we talked about in the last problem. So let's go ahead and find the critical value. I did it right there. I just heard myself do it, and I didn't even catch it until like a couple seconds later. It's a left tail test, so all of the alpha goes into the left tail. We don't have to divide it in 2. So 0.05 all into the left tail. We want to find that t-value that corresponds to that area. We'll do that using inverse t. The area to the left is 0.05. The degree of freedom in this case is n-1, which is 11 minus 1, which is going to be 10. So my degree of freedom is 10. And so I'm going to get, as my critical value, it's the only one, inverse t, 0.05, comma 10. We'll get negative 1.8, sorry about that, 1.812. And this time it will stay negative because this critical value is in the left tail, so it should be a negative value. So that's the critical value. The p-value we will find by taking the test statistic. So here's 0. The test statistic is negative, so it'll be to the left of 0. So negative 0.4861. And we want to find the area to the left tail, not because it's closer to the left tail, but because it's a left tail test. So we want to find the area to the left. So that area, which we will find with TCDF, the lower bound this time is negative infinity, so negative infinity. The upper bound is negative 0.4861. The degree of freedom is 10. And that is going to give me a p-value of, so negative 9999999, comma, negative 0.4861, comma, 10. And I end up getting 0.3187 if I round to 4 decimal places. And so that's the p-value. I don't need to multiply it by 2 because it was not a two-tail test. So that whatever you get from TCDF, that is your p-value if it's a left or a right tail test. You don't have to make any further modifications. All right, so what's my conclusion then? Well, if we use, so do I reject or do I fail to reject the null hypothesis? If we use the critical value, we draw the line here at negative 1.812. Zero's in the middle. My test statistic was somewhere in between, right? It was negative 0.48, what was it? 4861. So if it had crossed this line further into the left tail, that's when we would have rejected the null hypothesis. But it didn't. It stayed over here. So we will fail to reject the null hypothesis this time. Fail to reject the null hypothesis. So this is the proper initial conclusion. Okay, sorry, it's going to bother me. Let's try one more time. Okay. That's using the critical value method. If we use the p-value method, we compare the p-value to alpha. Alpha is 0.05. The p-value is 0.3187. That is greater than alpha. And if the p-value is greater than alpha, we fail to reject the null hypothesis. All right, so what is our final conclusion here? This is the last step, step 7. Our final conclusion is, let me get I was about to start typing on my calculator, but that's not going to work. So there is not sufficient evidence. All right. So if you fail to reject, it's going to be not sufficient evidence. Then you have to decide, is it to warrant rejection or to support? And that depends on whether the claim became the null or the alternative hypothesis. So in this case, the claim became the alternative hypothesis. So whatever we can say about the alternative hypothesis, we can say about the claim. We are failing to reject the null hypothesis, so we were unable to show the null hypothesis is false, which means we were also unable to show that the alternative is true, because the alternative is what would have to be true if the null hypothesis were false. We couldn't show it was false, which means we can't show that the alternative is true. And so there's not sufficient evidence to support the claim. We could not support the alternative hypothesis because we could not reject the null hypothesis. If we can't support the alternative, we can't support the claim because the alternative was the claim that was being made. So there is not sufficient evidence to support the claim that the mean radiation levels of cell phones, I don't know why it does that sometimes. That was really weird. Okay. Of cell phones is less than 1 W per kilogram, whatever that is. All right. Well, let's, again, probably on my stat lab, you're not going to have to type this in. It's going to be multiple choice, but they would put the 1.00, so I should do the same. So there was not sufficient evidence to support the claim that the mean radiation levels of cell phones is less than 1.00. Even though our sample was less than 1.00, the data just wasn't strong enough to firmly conclude that it definitely is less than 1. Right. So what would fix this would be to have a bigger sample size. I think that'd make a big difference. So we only had 11 data values in our sample. If we had like 30 or 40 and it was still, like the mean was still 0.93 whatever, then that'd probably be strong enough evidence to support the claim that it's less than 1. But with just 11, it just wasn't strong enough for us to make that conclusion. So that concludes the video on section 8.3. I'll see you in the next video for section 9.1.